Hi, this chapter is about clustering. And we're going to start from unsupervised learning because clustering is one type of unsupervised learning. And in clustering, there are many algorithms, machine learning algorithms. And in this chapter, we're going to cover just four algorithms: hierarchical clustering and the k-means, a mix of Gaussian and spectral clustering. And when we talk about the mix of Gaussian, we're going to learn expectation maximization algorithm, EM algorithm. Because EM algorithm is really famous and important learning algorithm in machine learning. Okay, unsupervised learning. So in this learning, we don't have label. We have only input X. So without the label, what can we learn actually? So obviously we cannot learn a mapping function from X to Y, right? From input to output. We cannot learn such kind of mapping because we don't have label. Then what can we do? So there are a couple of things that we can do. First, dense estimation. We already talked about it before. And then in this chapter, we're going to talk about clustering. And then next one is demand reduction in the next chapter. And we have a fact analysis. With the fact analysis, we're going to talk about hidden factors. Okay, the causes, important factors, and then the representation learning. So when we understand the data, we talked about the dense estimation. Right? In the dense estimation, I said if we understand the distribution, then we can understand the data, the population, and there are two approaches, parametric method and non-parametric method. And in the parametric method, we can think of Gaussian distribution. And in the Gaussian distribution, if we know a mean and variance, then we can estimate the Gaussian distribution. Okay. So basically, simple statistics would be helpful to understand the data. Okay, that's what we do. But there is a problem. What if the distribution is multimode, like this? Like this, we have two modes here. If we have just a single mode like this, then the mean and variance would be enough to understand this distribution. But what if we have a two? Then what should we do? Obviously, the simple statistics like average and variance are not informative. Look at this figure here. Okay, so when we have two modes like this, then if we calculate average is around here. Then average doesn't say much about these distributions, right? And the variance doesn't say much about this distribution neither. Then what should we do? These simple statistics are not informative. They don't talk much about the data. Then what should we do? This is where clustering comes to rescue. So if we have two clusters like this, and then in the first cluster, we have a mean and the variance. And in the second cluster, we have a mean and variance, right? So that is one way to do this. So let's talk about the clustering. As I said, clustering may help us to understand the data samples. Okay, then what is clustering? So roughly speaking, clustering is grouping samples in a way that the samples in the same group are more similar to each other than to those in other groups. Actually, this is what we do in our daily life. So think about your bookshelf. So you have lots of books, then how do you organize your bookshelf? Probably you do some clustering. You have some novels, and you have some textbooks, and you have some biography books, and you have some cartoons, etc. Right? So you organize your books based on the clusters. Also, we use clustering in many other cases. For example, you have lots of photos in your smartphone. Then how do you organize your photos? Probably you do clustering, right? Each of you might have different clustering. So some of you travel a lot, then you don't have just one travel category. You have different categories for different countries. But if you don't travel that much, then probably you have just one category for traveling, and so on. So we do this a lot, right? So in one group or one cluster, probably all the items should be similar to each other in a sense. And there is a difference between the items in a different group or different clusters. And for clustering, there are two basic issues. And the first one, which way would be more meaningful? So think about your photos in your smartphone. There are many different ways to organize your photos. Some of you might prefer some temporal kind of organizations, like based on the years, right? Or some of you might be interested in the locations, okay, or event. So there are many different ways to organize the clusters. So it is actually connected to this question. How can we measure the similarity? Which one is similar to which one? So it's up to you. You can define. If it is close to each other in time domain, then you can say, oh, they are close. But as I said, some might prefer the locations. And there is another one. How many clusters do we need? So let's take some example here. So in this figure, we have these green dots. Then some of you might prefer this clustering. So these ones and this one. So we have two clusters in this way. Or some of you might prefer this way. So we have four clusters. So uh, there are different ways to put some meanings here, or put some similarity. Or even with the same similarity, there is one question: how many clusters are more meaningful? So in this case, some people prefer just two clusters like this, or some people might prefer four clusters like this, right? So there's no correct answer here because this is unsupervised learning. So it's up to you. Depending on your definition of similarity, we can reorganize these clusters. And depending on your kind of level of specification, then we can define the number of clusters. And basically, we have a couple of approaches for clustering. First one is connectivity-based approach, and second one is centroid-based, and the third one is distribution-based, and then graph theoretic approach. So we're going to talk about the hierarchical clustering and k-means and mixed Gaussian, and spectral clustering is a little more advanced. First one is hierarchical clustering. So hierarchical clustering is really intuitive and really simple. And probably, I guess, you might use this approach in your daily life clustering. So we use dendrogram. It's like tree, okay, in the hierarchical clustering. So clustering is obtained by cutting the dendrogram at a desired level. And each connected components form a cluster. So it looks a little complicated, but it's really simple. So let's take an example here. So we have 9 items, and then we make a hierarchical clustering based on similarity. So based on similarity, these ones are quite close, okay? And then these ones are close, and these ones are close. And the next one is this one. This one is close to this one, and this one is close to this one, and then next one, this one is close to this one, and then this one and this one. So we can build up our tree based on this similarity like this, okay? So you can define the level of hierarchy, okay? So based on the level of hierarchy, like you can draw a line and then you can stop, or you can just define the number of clusters. Okay, then we know when to stop. Okay, we are going to talk about these issues in detail in the next slide. And basically, in hierarchical clustering, there are two different directions. First one is bottom up, and second one is top down. So bottom up means we have a lot of clusters. When we have n samples, then we start with n clusters, and then we actually combine the clusters from bottom to up. And the top-down approach is exactly opposite. So we have only one cluster, and then we split, and then we split again and split again until we have enough clusters. And let's talk about the bottom-up approach. So at each step, we have to compute the distances between all the pairs of clusters. Okay, and then we are going to merge the ones with the smallest distance. So when we have samples like this, then we have to calculate the distance from here to here and like this. So we have to calculate all the distances, and then we have to find the smallest distance. Let's say these two are the closest, then we merge these two. So now we have 4 clusters. We started with 5 clusters, now we have 4 clusters, and then we do the same thing. We calculate the distance. Okay, and then we find the smallest one. So the idea is quite simple and intuitive, and still there is a question. How to define the closeness between the clusters given a metric? This is the first question we talked before, right? So how can we define the similarity here? And especially when we have some clusters here with multiple samples, then there are a couple of ways to define the similarity. So first one, we can use the distance between the centroids. So when we have 2 samples here, then we can actually use the average of these samples. And then we can calculate the distance between this centroid to other samples. And if we have clusters like this, then we are going to use an average here, and then we can calculate the distance like this. Okay, that is one way. And another one is to use the distance between 2 closest points. So let's say we have one cluster with many samples, and we have another clusters with samples. Then this distance between these 2 clusters could be this one. Instead of using the average, we can use the closest one. And the last one, we use the distance between 2 farthest points. So in this example, this distance is the distance between these 2 clusters. So it's up to you. You have to define your distance. And also, there's another question are we going to use Euclidean distance? There are lots of types of distance metric. So you have to pick your distance out of many distance metrics. And then the second question is when to stop merging for a bottom-up approach. So you can define the number of clusters. Okay, so when we have 5 samples, if you only just 2 clusters, then we can combine these clusters until we have just 2 clusters. Okay, or we can just define some other kind of criteria to stop. So we can use cohesion, like impurity. So if the cluster is pure, then that's good. Like when we have samples like this, then if we make clusters like this, then it looks like these 2 clusters are quite pure. But if we have cluster like this, then this cluster is not pure. Well, we can define this impurity with some equations later in the decision tree. Anyway, we can define when to stop.